is yours and go ahead. Thank you.
So, hi everyone, my name is Bilal. I'm a BTech student from India at the Aligarh Muslim University. And today I'm going to present before you our study on the classification of motor imagery signals using machine learning. And here are the authors of the study, Anam, Hashmi, Bilal, and Omar, Farooq. So before I go into the specifics of what we did and how we did it, I would like to give you a brief background of this study. And so globally, there are like 13 million people who experience a stroke every year. Stroke is a neurodegenerative disease that blocks the blood flow to the brain, which may lead to partial or total paralysis or lead to permanent loss of motor movement. And globally, 1 in 4 adults over the age of 25 experience stroke once in their lifetime. So it's causing a loss of. So studies have estimated that it causes a loss of like 116 million years of healthy life each year. And so we decided that okay, as we are engineers, we really can't do much about it. But what we can do is we can help those who are working in this field, and we are trying to do our bit through this study. And there are actually quite a lot of studies that have tried to support this sort of thing through assistive technologies that range from fall detection for the elderly to brain controlled wheelchairs for the stroke patients or people with physical disabilities. And we are trying to work on such brain computer interfaces to develop a system that can actually use brain signals to detect the intention of the person or the person with physical disability who cannot move his hand or to grasp something or to do that sort of motor movement. So his brain functions are properly working, and we are trying to tap into that functionality. So how are we going to do that? Let's see in the next slide. So EEG is one such modality that's very popular for non-invasive method as a non-invasive technique. So what it does, EEG has electrodes placed all over the head of a person, where it just captures the electrical activity of the electrical activity when the synchronous neurons fire at a particular time. So it has a very good temporal resolution, but not much. It's not much good for spatial resolution. So since it's a kind of oscillatory sensor which captures the oscillatory motion of signals, it has different frequency bands. And currently we are looking into the motor imagery processes, which actually is like when an individual tries to imagine what he's going to do, then the brain actually mimics that sort of motion when he is actually doing that motion. So let's say if he's trying to move his hand, there will be some neuron firing in his brain. And instead of just moving his hand, if he just simply tries to imagine that movement, then the same sort of neurons will fire. And since the stroke patients cannot actually move their hands, what we are trying to do is use these EEG signals to support their motor movements. So through the external external mechanical devices. So this is just a part of that study in that direction. So these bands, as I have mentioned, that EEG has different bands. These bands start from delta, theta, alpha, and mu, beta, and gamma. For this study, we are specifically focusing on mu and beta bands because in the literature it has been said that motor imagery signal lies in the mu and beta band. And again, as EEG is not very good for the spatial resolution, we aren't too much focusing on which part of the brain would be would mimic, sorry, which part of brain would mimic the hand movement, which in terms of a spatial structure of the brain. But we are more interested in how, at what point in time did the person imagine his movement, and can we actually, using simple machine learning models, detect their intention to execute that movement or not. So for that, we have taken the data set from BNCI Horizon 2020, which was developed by University of Tubingen. So in their Germany. So in their data set, what they did, they actually recorded the data from a participant who has paralysis. So it was very natural and clinical in that sense, to what we are looking into, because some people might not. So, for example, a normal person might have some difficulty imagining that sort of movement, but a person who has that sort of physical disability has, because of constantly trying to move his hand, or trying to rehabilitate, or whatever, that sort of thing. So he would have much more brain strength in that sense. So what we decided to use that data, uh, and the data comprises of only a single participant. So that's one of the limitation of this data. And the way they have recorded is they shown the participant a cue, and when the cue is being shown to the participant is supposed to close his hand, close their right hands, and when there is no cue, they just relax it. So it's the tasks are very simple. There are two classes. The class one represents the closing of hands, while the class two represents the relaxation of hands. So this is what we try to classify. And if we are able to classify these two classes, we can potentially use these as control signals to control an external device to support their intention. And these are the contribution of the study, that we have accurately classified these two classes with a very simple algorithm. We have not gone for a very computationally expensive algorithm like deep learning or such, because our data is not, because we didn't have a lot of data as well. And what we did, we extracted some features and we tried to rank them, so to reduce the computational overhead, and we actually got very good results with just very few features. So I'll expound on these things as we go in this presentation. So this is our basic methodology. This is the pipeline that we followed. This is the pipeline that was suggested by Masato, and it's been used by many papers, by many researchers in this area. So what we did, we took a raw EEG. As mentioned, the raw EEG was developed by University of Tubingen in Germany, and it was from a person who had stroke. So it was very relevant for us. And then we pre-processed it using notch filter and wavelet decomposition. So we decomposed the signal into different bands, and then we extracted relevant features out of them. Sorry, the relevant features that we thought are relevant. But then we classified at this stage, and we found that, okay, our classification is taking a very long time. So what we thought, let's rank these features and try to take the features that are most relevant for our study, and then classify, and that has reduced the computational time quite a bit. And we used random forest for classification, and at the end we were able to classify these two, hand movement and relaxation, quite accurately. So this is the pipeline. This is just a basic general overview. And as I have said, again, I will expound on these different elements as we go along. So let's see the pre-processing. Let's see the pre-processing stage here. So for the pre-processing, we use notch filter to clear out the line frequency, and then we decompose the signal using wavelet decomposition. into different frequency bands. And as in the introduction section, I mentioned that we are looking into the new rhythm band and the beta band, which are relevant for us. And these lie in the range of 8 to 12 hertz to 13 to 30 hertz. This frequency band, these are the bands that have been suggested in many literature that they belong. These motor imagery, movement or motor imaging oscillation lies in these two bands, more or less. So we just went on with that, and we decomposed the signal using wavelet, using like a high pass filter and low pass filter. So we got these five coefficients. Our signal was the highest frequency was 100 hertz, and we composed into high pass and low pass, and then using this range, we decided to take those coefficients which lie in our desired frequency range, and then we went on to extract the features. So features are like the distinctive characteristic of signal, and it's like what are the most informative feature, or what are the most informative characteristics that would classify a signal from classify a phenomena from in one signal to the another. So we just took we went we reviewed the different literature. We tried to gather, okay, what sort of different things other researchers have used, which have produced the best results, and based on that, we tried to do a kind of an empirical thing there, and along with that, we just plotted our data on different domains and see which would be best for us. So it's just for the sake of representation and example, this is what our data looked when we plot the histogram. So we have taken a lot of statistical features to kind of based on this histogram. As you can see, we have taken interquartile range, median, median absolute deviation, variance, skewness, kurtosis, energy, mean absolute deviation, and standard deviation. So after so how we actually extracted the features, what we did after decomposing the signal, after getting the desired frequency bands, we took 1 second time window of the signal, and then we extracted these features for each time window, and then we repeated that process for the end, like till the signal ends, and we concatenated all these features for one class, and then we repeated that same process for the other class. So we kind of produced a feature vector space there. So we have one feature vector for a group of feature vectors for one class, and another group of feature vector for another class. And then we tried to simply do a classification at this stage as well, and we realized that, okay, it's taking a lot of time here because we had a lot of features, and most of these features have some sort of overlapping areas. Interquartile range and standard deviation might represent quite similar things. So what we did, we sort of ranked these features using a random forest method. And we found that the mean absolute deviation, energy, and standard deviation are some of the best features that we have. And we ranked them using like mutual information, how much information each feature is giving, like producing, or how much mutual information is giving out. And that's how we ranked these features. And we found, after taking different, so what we did, we took different combination of these individual features. So we took, so as you can see here, first we took the simply the mean absolute deviation, which is a mean absolute value, which is F3, and then we combined it with different with one other feature, then we combined with two other features, and so on and so on. And at the end, we got our results, which kind of look like this. So we have here a table where, if you can see, we have different feature combination, and we used random forest algorithm to classify in between these two classes. And as you can see here, that the classification accuracy is same for when we have selected 2 features and when we have selected 5 features. So it's more like some of these features are giving like same information in terms of classification. They are very much overlapping. So it's a good practice to just rank them, and to see whether taking these features that are producing similar, that are giving us similar information, would be just way too computationally expensive, and may not be very feasible in terms of realizing it in an actual in an external machine. So that's what our main concern would be was, and that's why we decided to rank them, and we ended up seeing that, okay, so just with simply 2 features, which were F3 and F4. F3 and F4 represents mean absolute value and variance, were the absolute best features that had given us the best accuracy. And the other combination that I produced, the second, the similar accuracy, was the combination of F3, F4, F8, F2, and F7, which were mean absolute deviation, standard deviation, energy, and let's just see, median absolute deviation, and 7. Yeah, and variance. So these two are basically the feature combination that have produced a similar classification accuracy. And you can see that it's very commonly reported that if you take more channels, or if you take more features in EEG signal processing or gas signal processing, you will get much better accuracy. But that sort of assumption fails in our case, as you can see here, that more is not always good. So these are the conclusion of this study, that we implemented a very simple algorithm, or a very simple pipeline that we followed through, and we got a very good results, and we were able to classify those brain signals that we can now use to control an external device. Sorry. And again, as I have said that we got very good accuracy from just by using two features instead of going for 5 features. So that would reduce the computational cost for our case very much, and it was very relevant for us, as we will be using this sort of thing on a very small microprocessor. So we needed that kind of thing. The other thing that we will be doing in future is that we have developed an external device, a prosthetic hand, if you may, and we will try to control that device with the control signals that we with the classified signals that we have now, and we will use those classified signals as the control for those for that external device. The major challenge and drawback of this study was that we didn't have enough data from real participants, or from real paralyzed participants, and we are now looking into that. We are trying to augment the data with the data augmentation technique, and trying to see if we can use some other data sets that may have similar level of participants. There are data sets. I mean, for simple, they have used normal participant for motor imagery. We aren't interested in those sort of data sets. What we are trying to look is, but can we gather data by ourselves, or is there data out there that have actually used real or paralyzed participants for this sort of thing? So this is the next challenge for us, and that's it for our study. And thank you. And thank you for your attention. If you have any questions, I'd be happy to answer.